In this presentation, we want to take a look at what tools Maple provides for obtaining power series and series solutions of ordinary differential equations. In particular, we're going to look at the second order linear equation. We want to consider both what Maple can provide directly and what tools Maple can provide to reproduce some of the classical by hands techniques that you see in a textbook. So let's begin with taking a look at some of the background information so that we know what it is that we're talking about. First of all, we want to discuss a regular point. So x0 is a regular point for this differential equation, linear second order, if the equation in the neighborhood of that point x0 has a power series solution. So this would be the representation of the power series, and we know that the coefficients therefore are derivatives divided by factorials. Now, if these coefficients a, b, c, and f are analytic in the neighborhood of x0, and also that a does not vanish at x0, then x0 will be a regular point, because if you divide through by a of x, these newly named coefficients p, q, and g, they will be analytic. And by repeated differentiation, differentiate the equation over and over again, you can compute the terms of the coefficients for the power series. So let's take a look at how that would go. Here's an example. I have constant coefficient equation, inert initial conditions, y at 0 and y prime at 0 are both 0. This equation clearly has an exact solution. This is the exact solution, and its series expansion shown here, at least the first few terms of it. So this process of differentiating and using the differential equation to generate the coefficients in the Taylor series is illustrated here. You can't see the equation. There it is. Okay. We know the first two coefficients. There's 0 because we picked inert initial conditions. Differential equation written y double prime equals, you would need to know these terms. Well, y prime and y at 0 are known. So you put those numbers in and you get this value, and you divide by the factorial and you have a sub k, which would be a2. For the third term, you differentiate this equation. You know how to take the derivative of the function f, or in our notation would be the function g. Y prime becomes y double prime. Y becomes y prime. But we know the value of y double prime because we just computed it. So you put the numbers in, you get a value, you divide by the factorial, and you have that coefficient, and you keep going. You take another derivative, so you have the fourth derivative. You know how to differentiate this. This becomes the third derivative, but you know the value of the third derivative because you just obtained it. You know the value of the second derivative because you have it from here. You get a number, you divide by the factorial, etc. Okay, and here's some code that would generate these numbers, minus 5, 8, 32, automatically. So it's doable. Now, the classical technique for obtaining the series has you substitute this formal power series into the differential equation. So for this differential equation, you would need to obtain the formal power series of the right-hand side. So that's e to the minus x in this case. Here is its series expansion. And then you take this series and you substitute it for y. Well, you need to take two derivatives. You're going to get n minus 1, x to the n minus 2 for the second derivative. For the first derivative, you're going to get n x to the n minus 1, and for the y term there's no differentiation. And you'll notice that the starting point for this series differs. This is starting at 2 because when n equals 0 and n equals 1, this term disappears. So you start the series at 2. And for this term, when n equals 0, that first term will disappear, so you start the series at 1. So there are 4 sums that you want to consider, and I've got them stretched across the top of this table. We want to get every x to have the same power. These two x's have the power n, but not these. So we make some manipulations to make them all have the power, which is the same. So we're going to let n minus 2 be the integer k, which means n is replaced by k plus 2. And that also means that when n is 2, k will be 0. So this sum will now start at k equals 0. This n became a k plus 2. This n became a k plus 2 less 1 is k plus 1. This n becomes a k plus 2. And this x is now x to the k. And you do the same thing here, except with a slightly different substitution. We want n minus 1 to be k. So n is k plus 1. When n is 1, k is 0. So this sum will start at 0. This n will become a k plus 1. This n will become a k plus 1. And this exponent will become a k. There's no change here except for the name. We let n be replaced by the integer k, n by the integer k. Now all of these sums start at the same point, k equals 0, and the exponent on x is the same, so we can write one sum and 1x to the k where we factor all of the coefficients, and this must vanish identically given that a0 and a1 are both 0. So this coefficient has to be 0 for every k. And that's what gives rise to the recursion, where we have set this equal to 0 and solved it for a k plus 2. So a k plus 2 is on the left, everything is thrown to the right, and it's here written with a minus out front. 4k plus 1, ak plus 1, 13 ak, and this coefficient from the expansion of e to the minus x, and then divide by k plus 2, k plus 1. And to get the coefficients, you would just make the appropriate substitutions for values of k and see what happens. So you let for k be 0, you have a0 and a1 are both 0. Do the arithmetic, you get a half. When k is 1, this will be a2, but you just computed that so you know what it is. a1 is 0, put the numbers in, you get a coefficient here. Notice how this becomes a 3, right? 1 plus 2 is 3, and this is a 1 plus 1 is 2, so 3, 2, then it's going to be 4, 3, then it's going to be 5, 4. You can see factorials appearing, all that kind of wonderful stuff. So, having obtained the recursion, put the numbers in, get the coefficients, and these coefficients match what we did up here by hand by using the differential equation to generate the power series. Now this is what Maple can do for us. Here's the differential equation. At least that's so far that's the left hand side. You want the formal power series for e to the minus x, so Maple has that as a convert option, or formal power series in x using n as the index, and so Maple can provide the formal power series for the right hand side. Then in the package, solve linear ordinary differential equation. there is a command, formal power series. You apply it to the differential equation. You must tell it what is the dependent variable, and this v of n will be the name of the coefficient in the series solution, and I believe it has to be v of n. I don't think you have a choice there. And this command returns what's called a formal power series structure. It contains two items. The first item up to this comma is a representation of the series. So there is the constant term, there is the x term, and then this series starts with x squared. This, when set equal to 0, gives the recursion. So this operand command reaches in here and grabs the second item from equation label 2, sets it equal to 0, and then we want to solve this eventually for the highest indexed v. Well, I want to use k as my counting index, but it comes out of this loop. We ran this loop up here. Way back here we ran a loop, and the index in the loop was k. So k comes out of the loop with a value. You can't use it anymore unless you unassign k. So I go in here and I say, you know, I want this series to start at 0 to be more familiar, so I'm going to let n be k plus 2. So I make the substitution, n is k plus 2. So this now reads v k plus 2. And so all of the n's are appropriately adjusted. And now I solve for v k plus 2. And I have this expression. Now the denominator looks like it could be factored perhaps. So what I did was I selected it, and in the pop-up that appears, you see you can factor that denominator in place, and you see next to it what the expression will look like if you do the factoring in place. And so you see the k plus 2, k plus 1, and if you want to compare this to what we got when we used a earlier, you'll see that it is the same, it's just written slightly differently. Down here we have the minus out front. Here the minuses have been moved to the numerator. There's your 13 a sub k. This factor, you can take the 4 out. There's the 4, it will become k plus 1. This would be the a k plus 1, and this term comes from the e to the minus x. This minus and this minus would make this plus, and it would match that term. And so this is what you get, k going from 0 forward. It turns out that for this example, this recurrence can be solved in closed form. And you use the rsolve command. So you apply the rsolve command to this recurrence equation, and you can see the form the recurrence equation has to take. Initial conditions, v at 0, 0, v at 1, 0, so I'm setting the first, this is the inert initial condition problem. Now when this solution comes back from this rsolve command, it will have the gamma function in it, and I wanted to change the gamma function to factorial, so I converted what would have been stuff with gamma functions into factorials. And then I hit it with eval c, because there were I, the imaginary unit, is in that solution. Even though it's real, it's disguised as a real expression. So eval c puts it into the form a plus bi, where the b is going to be 0, so you get just the real stuff. And you simplify and tell Maple this k is a positive integer. And so you get this expression, which is a closed form representation of the a's. And here is a sequence of some of these a's. And if you look carefully, you'll see that these numbers are the coefficients that we've already obtained several times already. Now let's consider the singular point. Solution about a singular point. Okay, what is a singular point? A point that is not regular is singular. In other words, if you can't get a Taylor series solution in the neighborhood of that point, then that point is singular. But singular points come in two varieties. The nomenclature here isn't really very intuitive, because the two varieties are called regular and irregular. So you have the perplexing phrase, the regular singular point. So in other words, you have regular points, you have regular singular points, and you have irregular singular points. So what's a regular singular point? The coefficients P and Q are not analytic, because if they were, then it would be a regular point. So the coefficients are not analytic. And we are prescribing how not analytic they can be. They have Laurent expansions. P has a Laurent expansion that starts at most with the 1 over x term. And Q has a Laurent expansion that starts at most with the 1 over x squared term. So P has a pole of order 1 at worst, and Q has a pole of order 2 at worst. That makes x naught a regular singular point. The irregular singular point is a beast of another color. Solutions in the neighborhood of irregular singular points are very hard to come by. They generally, you get asymptotic expansions in that vicinity. These are very, very nasty, and we're not going to consider them here today. We're just going to consider the regular singular point. Now, having obtained the Laurent expansion of P and Q, you form what is called the indicial equation. General form for the second order equation, r squared. This coefficient, less 1, is the linear, gives you the linear coefficient, and the coefficient q minus 2, which is the coefficient of the, or the lead coefficient of this pole of order 2, is the constant term. And this quadratic equation will have two roots. Call them alpha and beta, but they are ordered so that the real part of what you call beta is greater than or equal to the real part of what you are going to call alpha. Having determined that information, you can now state what the solutions in the neighborhood of this regular singular point could perhaps look like. One possibility is that you get a power series, a Taylor series multiplied by x to the beta. So that means this is a generalized series. It's not a power series because of this factor out front if this is not an integer or not a positive integer. There's a possibility that a second solution will exist with an x to the alpha out front of a power series. And then there's the nasty case where this solution might look like a logarithm times this first solution plus something that looks like y2. Now, there's always a solution of the form y1. So you always get one solution of this form. If you have a repeated root here for the indicial equation, beta equals alpha, then guarantee your other solution has the logarithm in it. If the difference between beta and alpha is a positive integer, then the second solution might be of this form, or it might be of this form, and the characterization of the equation that tells you which form you get is beyond what I want to talk about today. It's typically looked at in an intermediate differential equations course it's not relevant at the moment. Our equation here, here we'll see that in a minute, our equation will give us two of the better kind. We'll get a y1 and a y2, so we won't have to consider that logarithm solution. Okay, so let's take a p and a q of these two forms here, right? This is p is that's the Laurent expansion for it, so it's got one term from the Laurent expansion and one term from the Taylor part. And same thing for q, except it's a polar order 2. So this number 3/2 goes right there, minus 1. This number minus a half goes here. Clean this thing up, solve that quadratic. Beta is a half and alpha is minus 1. And the difference is not a positive integer. So you will get two generalized series solutions without a logarithm term. So if you take this p and this q, put it into the differential equation, and clean it up a bit, you will see that you want to multiply through by an x squared to clear this denominator. And here you have a half and a half and a half. So you're going to be multiplying by a 2. So that's why there's a 2x squared out here. And then the p term here, you have multiplied by x squared and a 2. So this will give you a 3x. And so you can see you have a 3x. And this is a 2x squared. This is going to give you a 2x squared. Right here, when you multiply by 2x squared, you're going to get this minus 1 surviving, and this will be a 3x. Okay, so what you now do is you look for a solution of the form Cn x to the n plus r. There's no sense doing the work twice with r being independently set equal to a half, and you go through all the calculations. Then you let r equal minus 1 and you go through all of the calculations. You use n plus r and you do the calculations once, and then you substitute the values for r at the end. So this is what the differential equation is going to look like when you make that substitution. For the second derivative term, you have an n plus r minus 1, x to the n plus r minus 2. For the first derivative, you get n plus r, x to the n plus r minus 1, and this is the no derivative term. Notice that n equals 0 remains the starting point because these were n plus r, not n. So when you clean this up, you find this x squared will come in here, and this 2 will go away, and you'll have an n plus r term. And here you will have two terms because it is binomial out front. This is an x squared. So this will go to n plus r plus 1. That's this term. And this will be a 3x. So the x will take care of this minus 1 power, and you'll have an n plus r term. This x will go in here, and this will go up to n plus r plus 1. That's this term. And the 1 will go out front here, and you'll have an n plus r. So you'll have 5 series to play with. 3 of one kind, 2 of another. N plus r, n plus r, n plus r. And I'll look at that in the left-hand column here. N plus r plus 1, n plus r plus 1. I'll look at that in the right-hand column. So I've summed those 3 terms, and you can see 1, 2, 3. And I did a little bit of arithmetic here, and I got it to this form. And since this exponent is n plus r, all I want to do is change the n to a k, because over here when I do some shifting, the n will become a k. So here I'll let n become a k, and I do a little factoring here, and I have this expression for those 3 terms in the series solution. So now I have to look at this fellow. It's n plus r plus 1, and I want n plus r plus 1 to read k plus r. So if I cancel these 2 r's, I have n plus 1 equals k, n equals k minus 1. And when n is 0, because that's what n starts out as 0, k will be 1. So this sum will become k equals 1. N will become k minus 1. N here will become k minus 1. And this n plus r plus 1 will become k plus r. I did a little bit of cleaning up here, and you get this expression. So now we can put some of this together. Unfortunately, this sum starts at 0 and this sum starts at 1, so what you have to do is extract the first term, the k equals 0 term, from this chunk before you can write one sum starting at 1. So you let k be 0, and you have an r, it will multiply at 2r, and this is a 2, and you take away 1. I factored into this form. C0 x to the r. And the rest of this stuff starts at 1, and you have these pieces, which are here, ck, and these pieces here, ck minus 1, x to the k plus r, must be identically 0. So all of these coefficients must vanish, as well as this coefficient. And that coefficient vanishing gives you the initial equation. That's where the initial equation came from. And if you do the arithmetic, you see that you have this plus 1/2 here and this minus 1/2 here, and we know what the roots are, that 1/2 and minus 1. So you take this stuff, set it equal to 0, and you solve for the highest ordered or highest indexed term. So ck is given in terms of ck minus 1. And this is in the numerator, and this stuff is in the denominator. And k will run from 1 going forward. So for the two values of r, you will get two recursions. And when r is a half, that's the beta value. I'll use b here. This recursion formula becomes this. And when r is minus 1, that was the alpha value, I'll use a, and this is what you get, and this cleans up, and this denominator cleans up a little bit, and you get this. And very pleasing to see the symmetry. Here it's 2k minus 3, here it's 2k plus 3, here it's k plus 1, here it's k minus 1. Okay? And then it's a question of just plugging numbers in to generate the coefficients one after the other. This says b1 will be a multiple of b0, and b2 will be a multiple of b1, but b1 was a multiple of b0, so b2 is a multiple of b0. And b3 is a multiple of b2, but b2 is a multiple of b0, and so b3 is a multiple of b0. And then you do the same thing over here for the a. a1 is a multiple of a0, a2 is a multiple of a1, but a1 is a multiple of a0, a3 is a multiple of a2, and a2 is a multiple of a0, and so a3 is a multiple of a0, and you can see how the coefficients get generated. Now, there are two solutions that we can write down based on this information. X to the beta, so that'll be x to the 1/2 or square root of x. Every term is a multiple of b0, so there's your b0, and then these are the numbers that we've generated: minus 4/5, 12/35, minus 32 over 315, etc. And for the other solution, r was minus 1, right? So x to the minus 1. So there's your 1 over x. Every coefficient is a multiple of a0. So pull that out, and then these numbers will show up: 1 minus 3/2, 5/6, and so forth. So that's what you do when you work by hand. Classically done for many of the famous differential equations from applied math. What can Maple contribute to this discussion? Here's the differential equation. The DE tools package has the command formal solution underscore SOL instead of the full word solution. You give it the DE, the dependent variable, the point of expansion, and it takes the parameter order equals. So you can declare how many terms of this partial sum is Maple going to display. And so you get two members of the fundamental set. They're separated by a comma. This is the one where r is minus 1 because of the square root. This is the solution where r was a half. And if you want to look over here and compare these numbers, you see that these numbers match these, and these numbers match these. Now, the dsolve command itself will yield a series solution, and so you can say dsolve series. But when you do that, you must make use of the global variable order with a capital O, and outside the command, change the value of that global parameter, and then you get a series solution. But this time the series solution has two constants, and it's the general solution, sum of linear combination of the two members of the fundamental set. I think having order as a parameter in the command is much more convenient. Again, Maple can solve this particular differential equation. So here is the closed form solution to this differential equation, and we want to get series expansions and compare to what we had done by hand. But the position of these two constants, underscore C1 and underscore C2, is not unique. They can be flip-flopped depending on when and how you do this calculation. And so here's some code that uniquely grabs each of these two solutions, calls one S1, calls one S2, and here I get a series expansion of each of these two solutions. This is the one with the square root out front, okay, and this is the one with the 1 over x out front. And again, if you look at the coefficients, compare them to what you see sitting up here, you get the same thing. Now suppose you wanted to use Maple as the tool for implementing the steps of the Frobenius method. What commands does Maple have available for that? In the DE tools package, there is a command singularities. You apply it to the differential equation, and Maple comes back and says regular singular point x equals 0. Irregular singular point out at infinity. So this is the regular singular point that we looked at already. And we can make use of the DE tools command indicial equation. There's the differential equation, the independent variable, point of expansion, the dependent variable. You get back the indicial equation, but it's given in terms of this variable x, and I would like x to be replaced with an r, and so that's what this eval is doing, is replacing the x with an r, so it looks familiar. And then I solve that indicial equation for r, and I get the two solutions, a half and minus 1. Now suppose we try this solve linear ordinary differential equation package command formal power series, and apply it as we did earlier. You get a formal power series structure, and this is what Maple says the series will look like. You should be on your guard immediately. This n is going to be an integer. There's no way that this is ever going to reproduce the solution with the square root of x. and you know somewhere's already going to have a half. It's not going to show up. You might get the -1 solution. You don't know what you're going to get at this otherwise. Okay, so this would set this equal to 0. This would be your recursion. So I grab it. Op is what operand, second operand here. Isolate this Vn, and in order to get some numbers out of this, the quickest way to do it is to see if Maple can give you a general solution. It can, so that's the rsolve command. I chose the initial condition, first term is 1, and then it comes back with, it's got gamma functions in it, so I convert it to factorial notation. So this is the general solution of this recursion, and I make a sequence of some of the values of this, and I say, okay, I have this. Now I go back here and I say, okay, then put that into this series, and I compare it to the series that it has to match, and that's the one that has the x to the -1 out front, and the coefficients are the right numbers, and I conclude that this formal power series command for the Frobenius method may not give me everything that I need. So now I want to consider the process of the stepwise implementation of the Frobenius method, and I want to see to what extent can Maple help me through that process. Okay, so I need the solution form that I'm going to use. So I use sum with a capital S, so it's the inert sum, x to the n plus r. And I want to plug it into the differential equation. And here's where you got to be careful. So first, I expanded the differential equation so that the binomial coefficients that was sitting here, let's run back and take a look at the differential equation. These binomial coefficients, like this thing here and this one here, that's what gets expanded. Okay? And then I plug in this solution, and this is what it ends up looking like. The 2x squared is out front, the 2x squared here is out front, 3x out front. I've got to get this x squared inside, because that x squared has to cancel with this x squared, and so forth. This 2x squared has to cancel with that x. So how am I going to do that? I have to massage this term differently from how I massage this term. So I want to grab each one of these 5 terms, and here's how I will do the grabbing. This sequence command makes a sequence of names, tt1, comma, tt2, comma, tt3, comma, so forth, and then the square brackets make that a list. This operand command applied to the left-hand side, because you see here is it equals 0. So I apply to the left-hand side. I get a sequence, but then it becomes a list of each of these operands. And because the plus signs, minus signs, split this into the 5 operands. Assign tilde puts the assign command onto each pair, right? So I assign tt1 as the name of this term, and tt2 as the name of this term, etc. So now I can address each one of these sums and do things to it. So what do I find that I need to do to it? And you poke around and you try this, you try that. So first of all, I needed to do an expand that gets this inside, gets the x squared inside. And then I want to pull all this together, so I need to combine. And then I need to simplify. Okay? And then this sum is n plus x to the n plus r. And all I need to do is change n to k. And that's what this command does. PDE tools dechange. It can be used for changing variables in a differential equation, in a sum, etc. This one, this goes to n plus r plus 1. So I need n to become k minus 1 after I do the crunching. This one, the x's will cancel, so this is an n plus r, so n only becomes k. This one, because of where this x is hiding on the right hand side of it, this goes to n plus r plus 1, so n has to become k minus 1. And this one, there's no change. So now, having made those transformations, I will rename the transformed sums, and these are just T1 through T5, and here they are. T1 will look like this, T2, T3, T4, T5. Now, this sum is starting at 0, this is starting at 1, and this is starting at 0, and this is starting at 1. So we have that same issue, that the terms starting at 0, there are 3 of them, 1, 3, and 5. They start at 0. You've got to pick off that first term. There is no simple way to pick off that first term. So there is a place where Maple could certainly provide some better tools, a way to take a series and say, I want to pull out the first so many terms and begin the series at the next term and not have to do all of this tedious op stuff. Because what I've had to do here is I've had to go in by op to grab the summand. So I did it for this one, and this one, and I added those summands together. Then I evaluated k at 0. That pulls out this stuff. And then I have to build all 5 sums, 2 that will start at 1, and 3 that I will now have made start at 1. And so I have to go to the summands, which is what I'm doing here, op, all 5 of them, add them together, and let k go from 1 to infinity. So this is the chunk that I get when I work by hand and have the series part, and then this is the part that gives you the indicial equation. Okay, so let's grab this recursion. Op to get in here, isolate the ck, do a little simplify, and now remember that there are 2 values for r, and you got those 2 values from r from the indicial equation, giving you 2 forms of the recurrence relation. Remember the symmetry here, it's 2k plus 3, 2k minus 3, k plus 1, k minus 1, and you'll notice that Maple plays around with the coefficients. Again, rsolve can solve the recursion for the general term. However, as we have come down through here, we have used subscripts on the coefficients. But the rsolve command for a recursion relation, it has to be functional. So bk has to be replaced by b of k. And bk minus 1 separately has to be replaced by b of k minus 1. There's no simple way to convert this form of the recursion, which is what you would write by hand, to Maple's functional form that you need for rsolve. And you have to do the same thing for here. And you get solutions. This is the solution for this recursion, and this is the solution for this recursion. And then I just tell Maple, okay, give me a sequence of values. This is the sequence of values from that recursion. This is the sequence of values from that recursion. This is the one where I use beta. Beta was a half, so this is going to be the square root one. And if you look at these numbers and compare it to the series that we have obtained earlier, you see that they match. This is the recursion that we get from letting r equal minus 1. So this is the series that's going to begin with 1 over x, and if you look at these numbers, they match what you get or what we got earlier. Now, it might seem that it gets a little dicey in here to use Maple to reproduce the stepwise commands of the Frobenius method. And I would have to agree. This is a lot of fiddling around. Is there a better way? Is there something that you can do with Maple that would make that a little bit less painful? And there is an approach that I first spotted way back in 1996, it's 20 years ago. It's in a publication that was called the Flight Manual, and it goes all the way back to Maple V. That was what it was called, Maple V Release 4. That was how they named Maple back in 1996. Here are the authors. Make this a little bigger because the last author is Dan Schwalbe. Dan was the differential equations guy here, and I have a suspicion that he's the guy that dreamed up this device. So what you do is you form a sum, not from 0 to infinity, but from one side of the general term to the other. And you may have to adjust how far back you go and how far forward you go in order to get what you need. So here I turned out that if you go 2 to one side, 2 to the other side of n plus r, so the general term would have a k in it, you back 2, go forward 2, put that into the differential equation, and a simplify brings all of the powers of x together. So you get an x to the k plus r, and you don't get stuff spread all around. Here, this term is x to the k plus r plus 3. Here's x to the k plus r plus 1. So those chunks are now all together. And you grab the coefficient of the x to the k plus r using the coefficient term. This thing will give you the recursion formula. And so I have gone up here. Here I grabbed it. The map is because this is equal to 0, and the coefficient command doesn't go across the equation here, so you got to look at the left-hand side of it only. Or you map to both sides and you get an equation with corresponding terms on each side. So set that equal to 0, which it will be because the map will pick up the equal 0. Then you isolate the ck. Then I hit it with a factor to make it look a little nicer. And we then compare this expression to what we got when we used subscripts earlier and worked by hand. And you can see ck minus 1, ck minus 1. So here's a minus out front, 2k 2r1, 2k 2r1, and this minus is now inside. And this is k plus r plus 1, 2k plus 2r minus 1, so they agree. So in my opinion, this device from the Flight Manual, going back 20 years, is the best tool that you could use in Maple if you want to obtain these results. If you really, really want to apply step by step the techniques of the Frobenius method that you would see in a textbook, be prepared for a bit of a go.